Let's discuss free fall. When air resistance doesn't affect the motion of a falling object, when the only force acting on the object is that due to gravity, we say the object is in free fall. Here we have a boulder, heavy enough that air resistance is negligible for short falls. Phil Physiker drops the boulder over the edge of a tall cliff. Since only gravity is significant, the boulder experiences free fall. We'll only discuss free fall here. The falling boulder picks up speed as it falls. This pickup is acceleration. Acceleration equals the time rate of change of velocity, given by the equation A is delta V per delta t. For straight line motion, we can use the terms velocity or speed interchangeably. Recall that speed is the magnitude of velocity. In free fall, during each second of fall, the exact same pickup of speed occurs. We say the boulder falls with constant acceleration. Here's Phil at the top of a cliff, ready to drop the boulder over the edge. He drops it, and it accelerates downward. Wouldn't it be nice if a speedometer were attached to Phil's boulder so that we could watch the gain in speed as the boulder falls? We wouldn't be able to see the readings, so we blow up the speedometer for better viewing. We start from rest, so the speedometer reading begins at 0. This is our initial speed. Our speedometer also has an odometer that measures distance traveled. Its reading is set to 0 at the time equals 0 mark. Phil releases the boulder with its speedometer, and 1 second later, the boulder is gained 10 meters per second during this 1 second interval. The odometer reading is 5 meters. That's 5 meters, not 10 meters, as we'll explain later. For now, just concentrate on changes in speed. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 20 meters per second. And our odometer reading is 20 meters. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 30 meters per second. And our odometer reading is 45 meters. And another second later, another gain of 10 meters per second finds the speedometer reading 40 meters per second. At the 4-second mark, we find our boulder has fallen 80 meters at the instant its speed is, as said, 40 meters per second. Let's make sense of these readings. First, the acceleration. We see that acceleration equals delta V per delta t equals 10 meters per second per 1 second equals 10 meters per 1 second multiplied by second, which equals 10 meters per second square. Notice how the symbol for second appears twice. First, the time and velocity, and second, the time during which velocity changes. That's why the second squared. How do we know that the acceleration of free fall is 10 meters per second square? Because we've measured it time and time again. You can do the same with actual measurements in the lab, where you'll get 9.8 meters per second square. To simplify calculations, we round this off to 10 meters per second square. We call the acceleration of free fall g. That's g for gravity. From g equals delta v per delta t, we can say that delta v equals g delta t, or simply equals gt, which reads, the speed gained in an interval of time t is equal to the acceleration times that time t. Since g equals 10 meters per second square, we can write speed gained as v equals 10 meters per second square times t. Notice how this equation accounts for the white speed readings. At 1 second, v equals 10 meters per second squared times 1 second equals 10 meters per second. At 2 seconds, v equals 10 meters per second squared times 2 seconds equals 20 meters per second. At 3 seconds, v equals 10 meters per second squared times 3 seconds equals 30 meters per second. At 4 seconds, v equals 10 meters per second squared times 4 seconds equals 40 meters per second. How about distance fallen? Here's where equations guide our thinking. From the equation for average speed, we know that distance traveled equals average speed multiplied by time. That is, d equals average speed times time, where average speed is v sub 0, our initial speed, plus v sub f, the final speed, divided by 2, multiplied by t. And we see our initial speed in this case is 0, and v sub f is the final speed at time t. And we have distance equals 1/2 gt times t, and t times t is t squared. So the distance fallen is 1/2 gt squared. Instead of d, we substitute y, the common symbol for vertical distances. For numerical values, distance of fall is given by 1/2 of 10 meters per second squared, which is 5 meters per second squared, multiplied by t squared. This agrees with the 5 meters, 20 meters, 45 meters, and 80 meter odometer distances of fall. Got it? Not really, until you've given some study time to this. In this lesson, we've considered the simplest case of free fall, starting from a rest position. Suppose instead that Phil Physiker throws the boulder downward, rather than dropping it. Suppose he imparts an initial speed, v sub 0, the speed when a stopwatch begins at 0. Our equations can take this into account. Instead of v equals gt, we say v equals v sub 0 plus gt. That is, the speed at any point will be the initial speed plus that gained by acceleration. And instead of distance y equals 1/2 gt squared, we add y equals initial speed times time. So the falling distance will be that due to an initial speed plus the distance it would fall due to acceleration. Getting back to falling from rest, initial velocity 0, I leave you with 3 questions. Question 1. At 5 seconds, what will be the speed of the boulder? 2. How far from the top will it have fallen in 5 seconds? And 3. What will be its acceleration at this 5th second? Think about that. Until next time, good energy. Here's Bullseye Bob holding his rifle in a level position, horizontally. Suppose at the same time he pulls the trigger, he drops a bullet from his trigger hand. Question: which bullet reaches the ground first, the one fired or the one dropped? Let's drop in on my conceptual physics class where I do a demonstration that features this activity. There's a little device here that will shoot a projectile. Little spring here. I'm going to compress the spring. And when I do that, I can put a projectile here and watch this gang, little spring gun. Okay. And out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of downish. This one goes outish. Now I'm going to do them both at the same time. And when I do them both at the same time, you guys got to figure out, hey, which one going to hit the ground first? The one that just dropped down or the one that goes out? A lot of people think, oh, the one that's fired out is going to be in the air for a longer time. You know why? Because gravity is going to start to pull it and say, oh, I didn't know you were moving, go ahead. And gravity not going to pull so hard. What do you guys think?
Let's try it. I tell you what. If you hear this, all A's. All A's. For this course, all A's. Registrar say, Hewitt, my God, Hewitt, you got all A's in your class. I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you gotta do your homework, okay? Here we go, gang. Here we go. This next moment may be very important for a lot of you who have your everything riding in your grade. All right, here we go. Here we go. Listen. What'd you hear? How many heard this? Wishful thinking. We'll do it one more time in slow motion. All right? Now you can get a better look this time. Slow motion. Here we go. All right? Same time, gang? Yeah. Gravity doesn't take a holiday on an object just because it's moving.
Back to our screencast. So we see that for a horizontally moving projectile, the time of fall is independent of what goes on horizontally. Horizontal and vertical components of motion don't affect each other. That makes sense. If you drop a pencil while standing in the aisle of a fast-moving airplane, the time taken to hit the floor isn't affected by the airplane's speed. Here we have Phil Physiker dropping a ball off the edge of a cliff. A tall cliff, very tall. We show the positions of fall at 1-second intervals. In the first second of fall, it falls 5 meters. 1 second later, it's 20 meters below the cliff. In 3 seconds, it's fallen 45 meters. And in 4 seconds, the ball hits the ground. It has fallen 80 meters in 4 seconds. Let's pretend there's no gravity and Phil tosses the ball horizontally. We see it travels equal distances in equal times. We're assuming no air resistance. But there is gravity, and the ball falls beneath these points. How far beneath? The answer is, interestingly, just as far as if the ball fell from rest at each point. The positions of the ball would look like this. When we join these points, we find the path of the ball is a parabola. Yum! Let's look at some velocities. First, vertically. An object dropped from rest gains a velocity, v equals gt. G is the acceleration of fall, 10 meters per second square. So in 1 second, its velocity is 10 meters per second. At 2 seconds, 20 meters per second. At 3 seconds, 30 meters per second. At 4 seconds, it hits the ground with a velocity of 40 meters per second. Oops, not enough space to show the full 40 meter per second vector, but I think you get the idea. Suppose Phil throws the ball at 20 meters per second. Then we have a 20 meter per second vector at each of the 4 positions along the green line. All these vectors are equal. 20 meters per second will be the horizontal component of motion along the parabola. We draw 20 meter per second vectors at each position. Next, we draw the vertical components. Again, not enough space for the 40 meter per second component. Then we construct parallelograms for each position. And with the parallelogram rule, we construct the resultant velocities at each position. Again, our lower vector runs off the page, but you get the idea, right? To calculate the magnitudes of these velocities, we use the Pythagorean theorem. V equals the square root of the sum of the components squared. We'll call the horizontal direction x and the vertical direction y. How much is the velocity at the 1 second position? It's the square root of 20 squared plus 10 squared. Your calculator will show you it's about 22 meters per second. How much at the 2 second position? Your calculator will show it's about 28 meters per second. And for the 3 second position? Your calculator will show it's about 36 meters per second. And how fast does the ball hit the ground? Your calculator shows it's very close to 45 meters per second. Once you understand the concepts, calculations can be fun. Yum? Let's take a look at what happens if the ball is tossed at an upward angle instead of horizontally. Watch what happens. Again, we first draw the ball's path as if there were no gravity, a straight line. And we show the positions of the ball for 4 1-second intervals. But there is gravity, so again, the ball falls beneath these positions. How far? Just as far as if dropped from rest at each point. This time our parabola has a different shape. How about if the ball is tossed at a downward angle? Note what happens. Pretty much the same physics. Is this yum or what? Now I want to leave you with a question. Phil Physiker stands on a raised platform and tosses a ball horizontally. The ball leaves his hand a vertical distance of 5 meters above ground level. His friends measure the ball landing 25 meters downrange. So my question is, what is Phil's pitching speed? How fast does the ball leave his hand? And the second question, how fast does the ball hit the ground? 2 questions. Think about them. Until next time, good energy. Phil Physiker tosses a ball across a field. We show sample positions of the ball at 5 locations: A, B, C, D, and E. We draw a vector at position A to show the initial velocity of the ball. At this position, the ball has just left Phil's hand, so no further throwing force acts and remains with the ball. Once out of his hand, the only force on the ball is that due to gravity, and the force of air resistance. To make the physics clear, we'll assume air resistance can be neglected. This vector has 2 components, a vertical one that changes due to gravity, and a horizontal one that remains unchanged as long as no horizontal forces, such as air resistance, act on the ball. At position B, we draw a shorter vertical component due to the loss of speed going upward. It's shorter than the component at A. But the horizontal component is the same as at A. We construct the resultant velocity vector at this point. At position C, at the top of the path, the vertical component has shrunk to 0. Only the horizontal component remains, which is then the vector for velocity at this highest point. Note that its length is the same as elsewhere. So how fast does the ball travel at the top of its path? 0 if tossed vertically. At other angles, velocity at the top is the same as the initial horizontal component of velocity, and the horizontal component at other positions. At position D, we have much the situation as in B. Same size horizontal component, but with the vertical component directed downward. So the resultant of these components gives the velocity vector at D. Note it's sort of an upside-down image of the situation at position B. And finally, much the same at position E. We're off the page here, but you get the idea. What we have is an upside-down version of A. The shape of the ball's path is a parabola. With air resistance, the path is not parabolic. It's something like this. The horizontal component in each successive position becomes smaller due to air resistance. We just show the horizontal components here. These smaller components are why the ball doesn't go as far downrange. And air resistance vertically means the ball doesn't reach the same height. Interesting? Let's get back to our ideal case without air resistance. The vectors we show are velocity vectors. We could also draw vectors for force, and even vectors for acceleration. Let's draw a vector for the force of gravity acting at the ball, say at position B. Shall we find the resultant of the velocity and force vector, say with this parallelogram? And what would the result be? The answer is nothing with any physics meaning. It would be rubbish. Don't do that. You can't combine velocity vectors with force vectors. They're different animals. To distinguish the two, we show force vectors in red and velocity vectors in blue. Phil Physiker says it well.
Take care with velocity and force vectors on the same diagram. They don't combine.
These red vectors represent the downward force of gravity on the ball all along the path. Although velocity varies along the path, we see that the force of gravity does not. It remains constant. The force vector is the same at all locations. Velocity vectors are one thing, force vectors are another. I want to lead up to a concluding question. We could as well have drawn acceleration vectors in this lesson, but we didn't. And a little thought will tell you that they'd compare well with the force vectors. After all, force and acceleration are directly proportional. Here's my question. What would an acceleration vector look like at the top of the path at point C? What would be the acceleration of the ball at this highest point? Think carefully about that. Until next time, good energy. Here's a problem that nicely makes use of the idea that horizontal and vertical components of motion for projectiles are independent. That an object moving horizontally is independent of its motion vertically. A horizontally moving tennis ball barely clears the net, a distance y above the surface of the court. To land within the court, it must not be moving too fast. Part A. Ignoring air drag, find the maximum speed the ball can have as it clears the net to land within the court's border, a distance d from the bottom of the net. To solve this problem, like most all problems, we focus on what is asked for. We're asked for speed, so we begin our solution by writing v equals. Just this much is a lot, for it puts us on the road to a solution. Model the tennis ball as a projectile moving in the absence of air drag, so the horizontal and vertical components of the ball's velocity are independent. We're asked to find its horizontal speed, so we write v equals d over t. D is the horizontal distance traveled in time t. We're given d, but we're not given the time. So this isn't a simple one-step problem. Importantly, the equation directs us to consider time, which we might not have considered otherwise. Now some important physics. The time t it takes for the ball to hit the court will be the same time as if we had dropped it from the top of the net from rest, a vertical distance y. We say from rest because the initial vertical component of velocity is 0, when the ball's at its highest point in the path, moving horizontally, just clearing the net. Our equation for vertical distance fallen from rest, y equals 1/2 gt squared. We see that the time is simply the square root of 2y over g. So substituting, we find our answer is v equals d over the square root of 2y over g. Yum. Let's put some numerical values in and ask, part B, calculate the ball's maximum speed as it clears the net of height 1.00 meters and that strikes within the court's border a distance of 12.0 meters from the base of the net. Plugging in the values, we see that the maximum speed for the ball is 26.8 meters per second. That's about 60 miles per hour. Try this yum problem with your friends. It's a good one. I want to leave you with a question. If the net were a little higher, would the maximum speed for the ball be a little less or a little more than 26.8 meters per second? Until next time, good energy.